Hello, and welcome to my TED Talk. Today, I am going to talk to you guys about bomb calorimetry and how it is used to determine the resonance energy of benzene. My name is Rose Anderson. So, the experimental process used in this investigation was calorimetry. The process is typically used in chemistry and physics to quantify the heat transfer in a reaction. A bomb calorimeter is made specifically to withstand the intense pressure produced in a reaction that involves burning fuel. The purpose of this experiment was ultimately to find the resonance energy of benzene using experimental and theoretical methods. The resonance energy is a measure of the stability created by the conjugated system with respect to the isolated double bonds. More specifically, I measured the heat evolved during the combustion of an organic compound in the presence of excess oxygen under constant volume conditions. In this specific experiment, I used the isodesmic reaction of benzene, pictured here, cyclohexane, and CDDT, because there's an equivalent sum of number and types of bonds. CDDT is used as a chemical intermediate for flame retardants, flavors, fragrances, and several other things. Cyclohexane is often used in cleaning products, in oil extraction, and as a component in motor vehicle exhaust. Since benzene is highly hazardous, we can use the experimental determination of the heat of combustion of cyclohexane and CDDT instead to determine the resonance energy of benzene. The experiment results in a series of temperatures for the course of the detonation of the bomb. The heat capacity of the calorimeter was determined using the known heat of the combustion and the weight of substance used. These two variables were then used to determine the change in internal energy of the combustion reaction of each molecule. We are able to convert this value into the reaction's enthalpy of combustion by adding the change in internal energy to the product of the molar change, temperature, and the gas constant, listed right here. Since all the processes are considered state functions, we can use Hess's law to determine the resonance energy of benzene. Here, we can sum the reactions and phase changes to determine resonance energy of the gaseous reaction that couldn't otherwise be determined experimentally. And here we have a list of these reactions that all sum up to get the resonance energy. So for a bit of context, just a brief summary of the experimental procedure used to determine the enthalpy of combustion of cyclohexane and CDT. First, we weighed an amount of each molecule into gel capsules. Next, the individual capsule was placed inside the oxygen bomb container and the bomb was charged through pressurization and placed in a water bath. Then we waited approximately 2 minutes for the system to reach its equilibrium before the ignition unit was connected. Finally, the bomb was detonated, and we waited for the temperature process to rise to a constant value before cleaning up the setup and weighing the leftover compounds. So my hypothesis for this experiment was that the enthalpy of combustion will be more negative for CDDT than cyclohexane because there are double bonds and more bonds in general requiring more energy to break. So ultimately, that the reaction will be more exothermic for CDDT than cyclohexane because there are more bonds to break, so there will be more energy lost to the surroundings. And my second hypothesis was that the resonance energy found in Cygress will be more accurate than those found experimentally because it involves a larger degree of data processing systems and just has a general higher degree of accuracy. There are also more variables considered. So in the data collection, there were 2 runs for each molecule, so 2 for cyclohexane and 2 for CDDT. This slide shows the data I found for the first run of cyclohexane, and here we have the graph of the temperature versus the time, with multiple temperature time points of interest noted. Ti is the time of the initial temperature, approximately 1 minute after the stirrer is turned on, so the system has reached its equilibrium. Ta is the time of the bomb detonation. Tb is the time at 60% of the total temperature change between point A and C. Tc is the time of maximum temperature, and Tf is the time of final temperature. On this table, we can see the relative time and temperature for each of these points, and down here we have the variable n value for the specific reaction, so the heat capacity of the bomb, the change in temperature, the change in internal energy of combustion, the change in gaseous moles, and the enthalpy of combustion. And we have this for each of our runs, so cyclohexane run 2, CDDT run 1, CDT Ren 2. So here's just a little reminder of and some context for how I calculated each of the variables in the tables in the previous couple of slides. So first, the important time temperature points were determined from the raw data. Then we have two different slopes that were calculated, one for the slope between the initial and maximum temperature, and then a slope between the maximum and final temperature. Then the temperature change was found using the aforementioned noteworthy time temperature points. Then the change in internal energy of combustion, which is equivalent to the total heat transfer, was found as a product of the bomb heat capacity and the change in temperature that was previously found. The molar change of the gas was found using the change in mass and molar mass of each molecule, where the mass was calculated, where we made sure to subtract the weighing boat and the gel capsule mass to get a final measurement of just the mass of the compound. And then finally, the heat of combustion was calculated using the internal energy of combustion, the change in gaseous moles, gas constant, temperature, and then in the tables previously, you'll see that the unit is in kilojoules per mole. So this was actually also divided by the change in moles to get that unit. Now that we have the change in enthalpy of combustion for CDDT and cyclohexane, the next component of Hess's law equation that we need to find the resonance energy is the enthalpy of vaporization of CDDT. Here we use the experimental vapor pressures for CDDT and fit the data to the Clausius-Clapeyron equation listed right here. And we can compare this to the equation of the line when we plot the natural log of P and the inverse of T. And we can compare these. So since the slope is given by negative enthalpy over gas constant, we can use this equation of the line to determine the enthalpy. So the enthalpy of vaporization of CDDT was found and listed in this table right here. I obtained the literature values for the enthalpy of combustion of benzene, enthalpy of vaporization of benzene, and the enthalpy of vaporization of cyclohexene from online. Then I took the average of the runs for cyclohexene and CDDT, plugged all the values into the equation I got from Hess's law breakdown, which I have right here, and got a resonance energy of 116.56 kilojoules per mole. So next I wanted to compare the experimental results from the calorimetry experiment with the more fine-tooth, hopefully more accurate experimental results from Cygress. And I got these values from Cygress, converted them from kilocalories per mole to kilojoules per mole, and put them into this equation here to get the theoretical resonance energy. Then I compared the two using the percent error equation and found a percent error of 17.21%. In conclusion, we were successful in finding the resonance energy of benzene using Hess's law and calorimetric bomb data for cyclohexene and CDDT. This indicated the experiment worked well for its purposes. The results showed that the first hypothesis was in fact correct. We can assume that the number and type of bonds that are in the CDDT molecule play a role in more heat being lost to the surroundings from the system in the reaction, or I guess in the combustion to be more specific. The second hypothesis was a little more difficult to determine a specific answer for. When we looked at the table on the previous slide comparing the two resonance energies, we see that the values are of the same magnitude and have a percent error of roughly 17%. While this is relatively high, it's still not an unreasonable error. This error can be a result of experimental error, but it could also be because there simply are just more variables and more precision considered in this Cygress setup. Because of this, I would recommend perhaps a further experimentation to compare the Cygress results to the experimental values. So this would involve having more trials for each molecule to see if the error I got was error in my experimentation, or if it's just the standard error or difference that there's going to be between raw experimental data and Cygress experimental data. There's always somewhat of a drawback with calorimetry that we need to note, and that the results are very reliant on the experimental setup, and it requires the maintenance of variables except the temperature to remain completely constant, so this can often be very difficult and brings up a point that could be targeted for further improvement. I also think that it would be interesting to explore the isodesmic reactions, or just explore other isodesmic reactions to see if they can be analyzed using Hess's law in the same way that we did for this experiment. So yeah, thank you so much for listening to my TED Talk. I hope you learned something, and these are my references. Thank you so much. Bye.